Today we will be doing the bovine shuffle brawn simulation problem. Convinced that happy cows generate more milk, Farmer John has installed a giant disco ball in his barn and plans to teach his cows to dance. Looking up popular cow dances, Farmer John decides to teach his cows the bovine shuffle. The bovine shuffle consists of his N cows lining up in a row in some order, then performing 3 shuffles in a row, after which they will be lined up in some possibly different order. To make it easier for his cows to locate themselves, Farmer John marks the locations for his line of cows with positions 1 through N. So the first cow in his lineup will be in position 1, the next in position 2, and so on up to position N. A shuffle is described with N numbers, A1 through AN, where the cow in position I moves to position AI during the shuffle. Every cow moves to its new location during the shuffle. Fortunately, all the AIs are distinct, so no 2 cows try to move to the same position during a shuffle. Farmer John's cows are each assigned distinct 7-digit integer ID numbers. If you are given the order of the cows after 3 shuffles, please determine their initial order. The first line of input contains N, the number of cows. The next line contains the N integers, A1 through AN. The final line contains the order of the N cows after 3 shuffles, with each cow specified by its ID number. You should write N lines of output with a single cow ID per line, specifying the order of the cows before the 3 shuffles. As you can see, this is our sample input and sample output. There are 5 cows. 1, 3, 4, 5, 2 is their final position after 3 shuffles, and each one of these is their ID. And the output is their starting position. To understand the backwards shuffle logic, first we need to look at the forwards shuffle logic. Now, for simplicity reasoning, I made each ID corresponding to some letter value. So we can see that in the input, our IDs will be A, B, C, D, E, and then our output will be A, E, B, C, D. Now, for our forwards logic, we can see that the initial order is A, E, B, C, D. That's why I use it as the initial. Well, what we can see is that A corresponds to 1, E to 3, B to 4, C to 5, D to 2. So whatever they correspond to is the new index that they will go to. So A looks at 1, so I'll go to 1. E looks at 3, so I'll go to 3. B looks at 4, so I'll go to 4. D looks at 2. Oh, C looks at 5, so it goes to 5, and then D looks at 2. Right, so this is what happens after the first forwards shuffle. If you do this 2 more times, you'll see that the result will be A, B, C, D, E. Because what's simply happening is that this goes here and then everything gets pushed back like this. This is just for simplicity case. It might not be for each one, but for the base case, this is how it works. And I'm just doing this for to quicken the video. But we could see that the final will be A, B, C, D, E, which matches what our input was. Because remember, our input is giving our final order, and we can see that our final order matches what the input is. And the key takeaway from this is that the shuffle value is equal to new index. This is what it will be for our forward logic. So now, if we want to do backwards, we have to do the opposite of this. So instead of shuffle value going to new index, our index value will point to the shuffle value. And now what does this mean? Well, we could see that for our backwards case, we'll say our initial list will be A, B, C, D, E, which is our final order. And we want it to go to our initial order, which is A, E, B, C, D. Well, what does that key takeaway mean? Well, we could see that in E's case, that E's index is 5. Well, if our index value points to shuffle, we know that E must go to wherever 5 shows up in shuffle by. And in shuffle by, the value 5 is at index 4. So E will go to 4. Now for D is at index 4. And in shuffle by, 4 shows up at position 3. So D goes to 3. C is at position index 3. And value 3 in shuffle by shows up at position 2. C goes there. For A, 1 and 1, so it just stays where it is at. And then E. E. And finally B. B is at position 2. And where 2 occurs in shuffle by is all the way at the very end. It is at index 5. So B goes here. Now, we just need to do this 2 more times. And this will lead us to our initial order. And to check if this works, what we can do is we set our result over here, whatever we find as our result, to our new list. So then it becomes A, it will be A, C, D, E, B. Now we can just calculate our results. Quickly doing it, we could see that B is the 4th, E 3rd, D 2nd, and then C comes all the way last. Now we need to do this one more time. So we have A, D, E, B, C. And then our resultant will be the following. C comes in the 4th, E comes in the 3rd, E comes in 2nd, and D all the way in the last. And does this make sense? Yes, it does. It matches our initial order. So as you can see, we went from the final order to the initial order. And what was the key takeaway? Key takeaway is that the index position that the ID is at will point to the index position of where the value is met in shuffle. So this index value will be the equivalent of this index value, because these two need to be the same. So now we can just implement this code. So in this code, we can see that first we're just taking sender input output. We get N as our number of cows. We get shuffle as whatever we're shuffling by, and then IDs as whatever the IDs are set to be. Now what Rev is doing is it's basically setting what our principal idea is. And that idea being the index that the current ID is at will be wherever the value in shuffle that index is at. So then we just see, well, it's just -1 for 0 indexing. And yeah, once we get that, we'll get 0, 4, 1, 2, 3. 5 is mapped to 4, or 5 is mapped to 0. 1 is 1, 3 is 3, 2 is 2, and 4 is 4. Right? So once we do that, now we have this for loop. And this for loop is just our 3 backwards shuffles. And new is just our new list. And then we just swap all the indexes over here. And then our final IDs is set to new. Once we keep doing that, after the 3 different backward shuffle, we'll get our initial position, which can be seen over here. If we rerun this, this is perfectly how it's supposed to be. We get the input case right. And then, yeah, you can see that this works for all of the cases.